Good morning, everybody. It's really my pleasure to be here today to give you an overview of the demonstrator that we set up at the EPFL, and that is operational since, I would say, almost a decade. So the topics that we are searching on this demonstrator are listed here, and they're quite different. The first one is about real-time situational awareness, essentially provide to operators, aggregators, and users that are having access to this power distribution infrastructure, the real-time knowledge of the system state. Then we are developing a machine learning-based forecasting methods for both loads and renewables, using different levels of time and space horizons. We are studying how to better interface megawatt class energy devices, can be energy storage systems or sources or controllable load. We are validating and developing centralized versus decentralized control schemes, where the control horizon ranges from days to intraday to real time, to the general IoT schemes applied to power systems, demand side management, and last but not least, self-healing grids. So essentially the possibility of disconnecting and back resynchronizing the system in case of external disturbances like local blackouts or large frequency or voltage disturbances on the main grid. Well, let me start with an overview of the infrastructure. The infrastructure has two layers. The first layer is a medium voltage layer. So here in this panoramic video, you see one of the feeders of medium voltage. Of course, the feeder is below the ground, which is interfacing the buildings of the Electricity Institute. And these buildings are all connected to the same system, along with a controllable megawatt class battery that is one of the main assets we are using, and also to some of the controllable demand that is composed by the ELL building, along with the electrical vehicle DC charging stations and level 2 charging stations that are on this building. So this is the battery I was making reference before. It's a megawatt class battery that can be operated as a voltage or current source. And I will come back to that part in a moment. The second layer of the infrastructure is a low voltage system that is inspired by a computer benchmark, a computer model that was defined by the SIGRE Task 466 back at the time by Professor Kai Strunz. What we did was to make it for real. So essentially, we have a one-to-one replica of this computer model, which is a one-to-one real system. Of course, it's entirely fed by renewables, in this case, photovoltaic systems. We have different types of load emulators, EV charging stations with different protocols, and 3 layers of energy storage systems, a supercapacitor bank, a battery, and a fuel cell, coupled with an electrolyzer and a nitrogen-oxygen storage system. Of course, these 3 energy storage systems are covering different types of dynamics, ranging from sub-second to weeks, according to the type of regulation schemes that you are interested to test. That's an overview of the infrastructure. So this is a picture of the low voltage infrastructure, in particular what we call the machine room. Now, let's talk about the functions that are embedded into the demonstrator, and in particular, I'm going to talk about time deterministic sensing via Phasor measurement units. So about the needs, the evolution of the whole power system infrastructure, as you know, is experiencing major needs, especially in the operational procedures, and in particular on the control and protection of the system. Now, there is a substantial need, which is the possibility of merging these two functions together. And there is an opportunity that is triggered by the availability of what we call Phasor measurement units, or PMUs, which are essentially devices that are producing synchronized sensing of a phasor, essentially current and voltage, amplitude and phases, frequency and rate of change of frequency. So essentially there are 4 measurements that are issued by these devices by using a common time source. And this common time source is in general provided by the GPS UTC time coordinates. So with these unique synchronization, you're essentially aligning not only the measurement, but also the phases of these phasors. So essentially what you have is to disseminate these PMUs on your infrastructure, synchronize the phases of your phasors using a common time reference. Here I'm referring to the GPS, but you can also use precise time protocols. Concentrate your data into a machine, which is typically located in the primary substation, and then feed set estimation, control, monitoring, and protection applications using a single infrastructure. There is a move in centralizing and merging these functions using this common infrastructure, as also seen by the evolution of the IEEE standards in this specific domain. Now, I'm going to be a little bit technical, so sorry for disturbing your lunch and your digestion, but you will see some formula here. Now, one of the problems in PMUs is that to extract the phasors, you have many techniques. Discrete Fourier transformation, wavelets, optimization based at Taylor series. Each one of these techniques has pros and cons, but the most used and the flexible one are DFT based. Why? Because they are computationally tractable, and these techniques can be embedded into a relatively inexpensive embedded systems, because we don't want to impact the cost of this kind of sensing infrastructure. Now, which are the main errors, main sources of errors into this kind of synchrophasor estimation techniques? The first one is aliasing. The second one is the long-range leakage. The fourth one is the short-range leakage. And the fourth one is the harmonic interference. Now, for which one of these main source of error, we have a sort of silver bullet. So for the aliasing, you just have to introduce adequate anti-aliasing filters and increase your sampling frequency. For the long-range leakage, you have to use appropriate window functions. For the short-range leakage, you can use interpolation of the DFT bins. And for the harmonic interference, you can do what we call iterative compensation of the negative and positive images of the DFT spectrums. I'm going to go a little bit technical now to show you how these issues can be solved using a single algorithm. This algorithm is relying on what we call interpolated DFT, which is essentially a technique which is interpolating the spectrum of your signal in order to estimate which is the bin, let's say the frequency that corresponds to the main component of your industrial frequency voltage and currents. As you know, the frequency of the system is never 50 Hz, it's continuously moving. And the problem is that when you are doing a DFT, you have only access to these black dots, okay, that are resulting from the superposition of the positive and negative image. Now, the question is how to estimate this green bin, which is actually the industrial frequency component you're looking at. Now, there is a possibility of estimating this delta, where this delta is the deviation from the maximum bin of your DFT with respect to the true location of the industrial frequency component that you're looking at. And there is a closed form way to compute this delta, which is given by the interpolated DFT. Now, the problem is that there is the interference, which is given by the negative part of the spectrum, but we have a solution, and the solution is to use the enhanced IP-DFT. So essentially, you compute your spectrum, you run the DFT once, you can estimate the negative image profile, and once you know it, you can compensate for it and re-estimate your bin. And this is characterized by a quite good performance in locating the bin correctly. We're talking about tens of parts per million. However, in case you have what we call out-of-band interferences, for instance, disturbances that are common in distribution systems, this technique behaves very poorly with respect to the red line, which is the limit in the errors, which is dictated by the IEEE standard. And you have to come up with another solution. So the solution is to use what we call iterative IP-DFT. How it works, well, essentially is more or less the same principle of the enhanced IP-DFT. So what you do is you compute your frequency spectrum, you run your IP-DFT enhanced to have a first estimation of your bin, of the maximum industrial frequency component. Then what you do is to look at the presence of an interfering component. And once you have located, and if you have located the presence of this interfering component, you remove it. And once you remove it from the spectrum, you rerun the enhanced IPDFT. And this is giving you essentially an algorithm which is robust against the presence of disturbing components from DC to 100 Hertz, what we call out of band interferences. Now, this table, sorry if I'm vomiting a bunch of numbers, is giving you the errors of this technique. These are not simulation. These are measurements carried out with a PMU calibrator. You're in the range of 0.0x%, okay? Just to give you an idea. So we are in the range of parts per million, the estimation of the phasors. And in terms of estimation of the frequency, we are in the range of milliards or fraction of milliards, okay, as a function of the signal to noise ratio. Now, these devices are real, are not just a computer exercise, and have been installed pervasively in the whole FFL network. And here you can see some of the installations where you have the PMU device. For the measurements, we are using Rogowski coils for the currents and capacity voltage dividers for the voltages. And here the telecom that is relying on different technologies, cabled or wireless, according to the location of the device. What do we do with these devices? Well, essentially, we are feeding what we call real-time situational awareness. Let's say, what do we call state estimation? Now, we have different algorithms that are running on the campus. A static state estimator that can run both least square or least absolute value methods. As you know, these methods are called static in the sense that together with the network topology, they only use the current measurements, current, I mean, at the current time, plus their uncertainties to estimate the system state, which is composed by the phase to ground nodal voltages. We also have other algorithms that can be used in our state estimation process, which are essentially recursive state estimators like Kalman filters. You know, Kalman filter has the advantage of using what we call process model, which is an early time forecast of the evolution of your system state. And we have developed quite interesting techniques to make this process model accurate and exact. Of course, if you have the same type of measurements and information about the network topology, you can formally demonstrate that any recursive state estimator is always superior to the corresponding static state estimator, provided that the process model is exact. And we can play with these methods as we want into the demonstrator. So essentially, this is the sensing infrastructure. We have the possibility of measuring flows of currents, nodal voltages, or injection, depending on the substation that we are targeting. And of course, the measurement model changes accordingly to the type of measurements. As I said, the sensors are composed by capacitive voltage dividers, and the current sensors are Rogowski coils. So how the workflow of the state estimation proceeds, it's very simple. So we are collecting zero injection buses. Zero injection buses are interconnecting nodes where you have no injections. We may use also pseudo measurements if we want, but mainly we rely on PMU measurements. We sense the breaker statuses to have that are feeding up topology processors. And essentially, we run an observability analysis. The observability analysis essentially is telling you whether the measurement model has a full rank or not. If it is rank deficient, we cannot carry a state estimation. So we carry the state estimation algorithm, and then what we do is that we are checking the presence of bad data in case we are using a least square method. If you're using an LAV, of course, bad data is embedded into the process. And in case we detect bad data, we are removing them and we are rerunning the state estimation. Okay. So this is an example of estimates of the state. So essentially, you have the nodal voltages and angles. You can see the comparison between the measurements and the estimated states using different algorithms. WLS, so least square estimator, or a discrete Kalman filter. You can clearly see the filtering capability and the compensation of the offset due to the offset that was eventually present into the measurements. You can also see how the state estimates can follow step changes into the state. These step changes are essentially due to variations of the voltage on the slack bus of the system due to step variations of on-load tap changers of the main transformer feeding the EPFL campus. You can see how we can reliably track the evolution of the system state even in the presence of steps, which is a very challenging problem. I will not go into the details because I don't have much of time. Talking about latency, the latency of this process is composed by 4 main blocks. The first one is into the PMU. So you have the acquisition window, the estimation of the synchrophasor, the data encapsulation, which is then sent to the network. And this is the first latency. The second one is about the telecom. And the third one is about the PDC, so the phasor data concentrator, and the estimation of the state itself. So these are the cumulative distribution functions of this latency. So you see the first one is into the PMU, is very time deterministic, simply because we are using FPGAs into the PMUs, and which are time deterministic computational platform. The same thing is for the TCU. And then when we go into the network, you see that the network is introducing some spread of the delay because we are entering the network of the EPFL. Again, we are within a pretty time deterministic computation. So essentially, within 70 milliseconds, we conclude the whole computation. That's a fixed delay. That's a worst case delay, if you want. And we do this each 20 milliseconds. That's a refresh rate of the system. What do we do with this data? Well, we can feed control, but the very first thing that we do is to feed forecasting. And essentially, the possibility of feeding forecasting is allowing us to do a dispatching of the infrastructure. So the first thing is about forecasting. So what we do is that we are looking at the historical data from PMUs in our historian. And then what we do is that we are disaggregating this data by separating the load from the PV. I forget to say that on campus we have an injection from photovoltaic panels that is summing up to 2 megawatts. What we don't know, or what we pretend to not know, is the amount of PV installations in each building. So since the PMUs are measuring the aggregated injections and consumptions of the building, what we do is to disaggregate these time series by separating loads and injections. How, again, I don't have time to go into the details, but essentially is an optimization process that is essentially minimizing a metric, which is the similarity between the aggregated measurements and the injected PVs, knowing, having the notion of the measurements of the GHI. So once we have done this separation of the clusters, we are training a forecasting model for the load, and we are separating the forecasting tools for the loads according to the type of the day, the period of the year, and let's say the possibility of having special days. Special days are essentially vacation days. Then what we do with these scenarios for the loads is that they are sampled, and they're sampled in order to be fed into the dispatching tools. The other process that we're feeding once we do the disaggregation is to have the notion of the PV configurations that we have in each building. And these PV configurations, provided the day ahead GHI forecast provided by MeteoTest or MeteoSwiss, which are the two services we are using, are giving us the opportunity of generating scenarios, because these forecasts are not only giving you the day ahead average GHI, but also the corresponding coverage intervals. So we can generate scenarios not only for the loads, but also for the PV. So what do we do with these scenarios? Well, essentially, we solve an optimization problem that you see here. Sorry again to show you equations, but essentially, we wanted to determine a profile of the aggregated power of all the buildings that is controlled by the injection of the power of a controllable asset that is a battery. And this battery, of course, has to satisfy constraints, and these constraints are multiple: energy, power constraints. It has to satisfy also the constraints of the grids in the form of an optimal power flow, as well as the constraints of the power factor that we have at the point of common coupling with the upstream grid. And this problem is solved for all the scenarios that we are sampling into the system. Now, in the objective, you can have multiple objectives. The first one is to, of course, define this dispatch plan. The second one can be also to have a sort of self-consumption into the system if you want, or minimize the injections of the controllable assets, in this case, the battery, for reasons associated to the aging of this device. For instance, if you have a cost function that can weight also the aging due to the cycling of this battery. That's a general category of problem that we are solving day ahead. And of course, that will be solved for all the possible scenarios. So essentially what you do is you come up with this kind of outcomes. So you have for all the possible scenarios, the day ahead scenarios using the PV and load forecasting. And this is the output, is the red curve, is the dispatch plan. The dispatch plan is essentially a profile that you are selling to the market, you're advertising to your balancing group or to the market. And what you do is that you can guarantee that for any one of these scenarios that can be realized, you can have multiple trajectories of your controllable asset, in this case, the battery, such that you can always stick to the dispatch plan that you negotiated with the system. Okay, that's the exercise that we are doing. And what you have to do is that you have to guarantee that for all these scenarios that you are throwing into your optimization process, your problem is feasible, not only for the controllable battery, but also from the grid perspective. Now, I'm showing you the implementation of this dispatching into the low voltage infrastructure that I was mentioning before. And this is what you get. So essentially, the black curve is a dispatch plan. The gray curve is the realized dispatch plan. You can see that is practically superposed with what you established a day ahead. And the red curve is the realization without the control that you implement with this technique. Now, the interesting thing is that in the intraday, so essentially in the moment you start to track the dispatch plan, we have an MPC. And this MPC is essentially leveraging early time forecasts of both load and PV in order to take a decision, an anticipative decision, in order to not violate the system constraints. For instance, in this experiment, again, this is not a computer simulation, it's a real experiment. You can see that the battery was reaching its maximum capacity. And the forecasting of that was used by the MPC was forecasting larger production from the PVs of what was computed the day ahead. So the decision that was taken was to curtail the PV in order to avoid the SOC of the battery to reach its maximum. Okay, that's an example of how the MPC can work in order to avoid the violation of the system constraints. Again, the objective here was to track the dispatch plan, and indeed you can see that the tracking was guaranteed with very high fidelity. Now, this is a subject where we have spent a lot of time and a lot of efforts, which is about agent-based real-time control. Unfortunately, I will not go into the details. Perhaps we can discuss this into the Q&A session. Instead I'm going to show you is the clustering of ancillary services. Why this subject is of interest? Well, essentially because I have shown you the dispatching exercise, but then you can ask yourself, well, I have in my system, in my distribution system, several flexibilities, for instance, electrical vehicles, batteries, controllable demand, and I can do day-ahead dispatch. And if my forecasts are good enough, I can have the quantification day ahead that some of the energy availabilities of these controllable resources are unused in the next day. And this I can quantify day ahead. And the idea is, why don't I use these leftover flexibilities to sell, to provide ancillary services to the system? For instance, frequency reserves. And this is what I'm going to talk about. So I'm specifically referring to the case of assets that can interface with the system using grid forming capabilities. Why this is interesting? Well, essentially because together with the provision of frequency containment reserve, dispatch, and reactive power control, which are services that a grid following interface power electronics can provide, grid forming devices can also provide inertia. Okay, and this is the biggest advantage that this type of interfaces can provide. Now, I'm going to show you how we have framed an optimization framework that does exactly this. So essentially, in day ahead, what you do is that you can compute what we call energy and power budgets, which are essentially the amount of energy and power that you need all along the day for all your services. And for instance, this can be dispatching, primary frequency control, or secondary frequency control if you want, voltage, reactive power support, for instance. And in day ahead, essentially, you solve the classical problem that I was showing you before. But in this case, it's slightly modified in the sense that you have to have two additional constraints, which are essentially embedding the worst possible positive and negative realizations of your service. For instance, in this case, L arrow up and L arrow down are essentially taking into account the worst positive and negative realizations of the aggregated load and PV generation that I have in day ahead. And you have also to add your power needs associated to, for instance, primary frequency control, okay, which are in this case linked to the droop of your system. And once you have solved this problem, you can have the notion of how much power and energy you allocate for each service. Then in the intraday, what you do is that you have established these reference powers for active and reactive power that are tracking this day ahead trajectories that you have established. However, in the intraday, you have errors, and these errors are coming from the fact that what you forecasted day ahead is not necessarily true. Also, the frequency that you consider a day ahead is not necessarily true, and you can have biases in the provision of regulation services due to the frequency. And what we do is essentially to adjust this tracking by changing the references of frequency and voltages of our voltage source converters. And this we do in a shrinking time horizon using an MPC, and this shrinking time horizon has typically an amplitude of 5 minutes. Of course, is usually defined. The very last point that we are considering is the fact that the capability curves of your converters are voltage dependent. So we are solving another optimization problem to retrieve feasible operating conditions for the power converters. But again, I'm not going to talk about this because I have a limited amount of time. So we are applying this to one of the medium voltage feeders of the PATHFNDR campus that you see here represented in a schematic way. And this is exactly what I was telling you before. So you can see the budgets which are allocated to the uncertainties of your PVs and loads associated to the scenarios that you are drawing day ahead. And you can see that if you look at the integral of these power budgets, which is giving you the energy budget hour by hour, at the end of the day, you have a leftover energy that you can always use for other services. In this case, the provision of frequency containment reserve. And the optimization problem is also telling you which is the optimum value of the droop in the form of power over hertz that you can provide given this leftover energy you have into the system. So this is the true experiment. You can see the energy that was used to track the dispatch plan and the energy, positive and negative, that was used in order to compensate the frequency fluctuations. So here you can see the frequency fluctuations all along the 24 hours. It's interesting to see that the frequency exhibits these periodic changes that are synchronized at each hour. This is due to the incapability of the market of having a perfect clearance at each hour. And here you can see the evolution of the state of charge of the battery. So this is an example of an experiment that was carried out with this infrastructure. It's also interesting to show the superior performance of grid forming versus grid forming versus grid following when you look at the relative ROC-off. What is a relative ROC-off is essentially the variation of the local frequency that we are measuring with our PMUs with respect to the variation of power due to primary frequency containment reserve. Okay, and you can show that if you're using grid following, which is essentially the red curve. You have a CDF, which is way more dispersed. Instead, if you're doing the same type of control using a grid forming, you see that the relative rock-off is way more stiffer and centered around 0 Hertz per second per watt. Saying that with the same type of primary frequency control, a grid forming system is providing way more stiffer frequency control to the local system, speaking in favor of the usage of this kind of power electronics to enhance grid stability. Now, this is what we are doing is a subset of activities. Again, I can talk for the rest of the day about the experiments that we are doing, but let me talk about what we are doing in the Pathfinder. So in the Pathfinder, we are essentially using the concept of day-ahead markets in Switzerland and balancing groups. You know that balancing groups in the Swiss market are not geographically tight. And essentially, what we are interested to do is to leverage a multi-grid, multi-microgrid structure where we are using the platform at the FFL and the EMPA platform in order to mutualize flexibilities into geographically untighted microgrids. So essentially, if I'm running out of resources in my system, in my microgrid, I can mutuate what is available at EMPA and vice versa, such that if we are both participating to the same balancing group, together we have a better performance than being separated perhaps in 2 different balancing groups. And this is essentially a slide which is showing schematically what we're expecting to do. Okay. Essentially, what we are doing this, we are implementing this via a day-ahead dispatching problem, which contains coupled constraints of the multiple microgrids that we are representing, and of course the possibility of having aggregation of forecasts of the flexibility that we have into the multiple microgrids, and of course we are also implementing an MPC that is distributing the set points on the multiple microgrids which are connected on the same that are sharing their profiles on the same balancing group. So this is an example of a simulation where you can we have two microgrids which are sharing the same medium voltage infrastructure. Of course, in our case, we will share the whole transmission grid that we have in Switzerland. But the interesting thing is that if you look, we force the scenarios of one of the microgrids to be unfeasible. Essentially, you have scenarios that are you have uncertainties in tracking with high fidelity your dispatch plan day ahead. When you are mutuating your flexibility, actually you move from this figure to this figure. But essentially, you can guarantee with a very high fidelity that you're tracking your aggregated dispatch plan because you're mutuating the flexibilities of these geographically untight distribution systems, or in this case, microgrids. So final remarks. The Smart Grids platform is an ongoing live project that is essentially used to develop and validate control and sensing techniques to support sustainable management of stochastic energy resources, power facilities, and eventually end users. We have developed it in order to be an advanced model for students, research staff, and industry, as well as authorities and general public, to support development of these technologies with specific reference to power distribution systems. Now, the involvement of this platform with the Pathfinder project is targeting the demonstration of how to coordinate multi-size and multi-time dispatching of geographically distributed microgrids that mutualize power and energy flexibilities that are made available by fully controllable and stochastic energy resources. With this, I finished my talk, and I will be more than glad to reply to your questions.